Hey, it's time for chapter 4, variability. All right, let's get right into this. So in order to introduce the concept of variability, I want to talk to you about some social psychology research on face attractiveness that hopefully you find a little bit interesting since you're psychology majors. In this study, researchers were interested in what makes a face attractive. And so they presented students with computer-generated images of faces. And so that's what you see right here. And these pictures had been created by averaging together actual photos of completely different people to create a composite, right? So some of the composites were created from 4 sets of real faces like this. So this is the average of 4 different male faces. This is the average of 4 different female faces. 8 faces, 16 faces, and then finally 32 faces, right? So these are the average of 32 different female and male faces, respectively. Now, one of the things that happens when these composites get created is that some of the unique features of different faces ends up getting washed out. And this becomes the case more and more as the number of faces used to create the composites increases. So when the researchers averaged across only 4 faces, right, like what you see here on the far left, there was still some room for individuality, right? Like some faces were round, some thin, narrow, some had large noses, smaller noses, etc., right? But when the researchers averaged across 32 different faces, well, they ended up with composites that were very average, right? So in other words, the placement of eyes, nose, ears, size of the features, it was pretty much the same across the composites, even when 2 completely different sets of 32 photos were used. All right, they then asked students to rate the pictures on a 5-point Likert scale. And these data show the average rating across all participants for each picture in the 2 categories, right? So I'll just show the 4 face and 32 face, right? And researchers' main interest here was in the central tendency, right? They wanted to compare mean attractiveness between pictures averaged from 4 faces compared to 32. And as expected, 32 face composites were more attractive than 4 face composites, right? So faces with distinct characteristics, in this case, were less attractive than ordinary or average faces. But in addition to central tendency, right, in addition to these means, you can see in these tables the 2 sets of scores also differ in another way, right? And that is, if you look across the data, right, for 4 faces, look across the data for 32 faces, they differ in terms of their variability. It's just by looking at this, you can see that the ratings for the 20 different pictures comprised of an average of 4 faces for each picture had a lot more of a spread, right? There was a lot more variability in ratings for those, whereas the 32 face pictures, the ratings were consistently similar across all the different pictures, regardless of the 32 different faces that were used to make the composite. This really becomes clear if we look at the data in a histogram, right? So here's the average of 4 faces, here's the average of 32 faces. You can really get a sense of how widely distributed the variability was for the 4-face composites compared to the 32-face composites, where the variability was dramatically restricted. So the descriptive measures that we've talked about so far, right, central tendency is what we've talked about, mean, median, and mode, they don't speak to how we measure this variability. So with chapter 4, we're going to discuss a couple of different measures that can reflect this difference in variability. All right. So on the very first day of lecture, right, the first video you watched, I stated, and I've probably stated this several times since then, statistics helps us determine why there are differences among individuals and whether these differences are useful or are they trivial. Now, in statistics, you can look at it in the sense that it's almost as if we're trying to explain variability between data sets. So look at these 2 examples that I have on the slide. I've got just some phony made-up data of exam scores for exam A and exam B. And I would ask you to answer this question. Do you think that these 2 sets of numbers tell the same story? Well, one thing that should stand out is it looks like the scores for exam A are more spread out than the scores for exam B, right? much like our face data from the previous slide. Like there's more of a width of values, ranges, if you will, on exam A than exam B. But really what I'm getting at here is, do you think these data sets are different from one another? And at this point, most people say yes, right? If I'm teaching this in sort of an in-person class, I put this question to the class, and most people look and go, well, yeah, the variability clearly is different between the two samples of the exams. So let's really start to try and answer this question. What I want you to do is I want you to figure out the mean, median, and mode for each of these data sets. Okay, so I want you to do it for exam A. I want you to do it for exam B. Mean, median, and mode. Go ahead and pause the video. And when you come back, I'll move on to give you the answer. So you can see, as I'm sure you figured out, that the mean, median, and mode for exam A is 75. And the mean, median, and mode for exam B is also 75. Right? So all three measures of central tendency for both exams were the same exact value. So here you can see that two different sets of data can have wildly different values, and yet they can have the same measures of central tendency. So quantifying the variability, right, because clearly these data sets are different, quantifying that variance, quantifying the variability helps us use measures of central tendency to better describe our data. So variability, it's a measure of dispersion or distance, right? Measures of variability help describe a distribution. They give us an idea of how well a single value represents the entire distribution. So if you have a lot of variability, it might be difficult to accurately describe an entire data set with a single number. But variability, no matter sort of which value we use for it, right, which measure we use to describe variability, it's still a descriptive statistic, right? So it describes the overall dispersion or distance between scores in a data set. So it's a very important component for inferential statistics. We will also use a specific measure of variability that we learn how to compute today called the standard deviation. You'll find that we use that much like we'll use the mean in many of the statistics that we will learn how to run this semester. So it's a very important measure in statistics, generally speaking. Now, there are a few ways that we can measure variability. Again, I'm only going to talk about a couple here. The first one is to just look at what we call a range of scores. And one of the questions on the homework is going to deal with range. So make sure when you answer that question, you're using the correct formula. And note that there are two separate formulas, which I'll get to on the next slide. Now, why do we have two formulas for something as simple as range? Well, it has to do with whether or not your data is discrete or continuous. So remember, discrete variables are variables of data that consist of separate, indivisible categories. So no values can exist between neighboring categories. So example would be the number of red marbles in a jar full of marbles, right? There's not going to be 15.3 red marbles. There's going to be 15, right? Because it is an indivisible unit. The number of television sets that you have in your home. You might have 0 TVs, 1, 2, 3, right? Whatever, but you don't have 3.7 televisions. The television is an indivisible unit. It is a discrete piece of data. And so if you are computing the range for discrete data, you simply take the highest score minus the lowest score. So it's quite simple. Conversely, if you're computing the range for continuous data. And remember, continuous data can have an infinite number of possible values fall between any two observed values. So it's divisible into a number of fractal parts, right? And the level of specificity or precision, actually is the better word I'm looking for. Our level of precision is dependent upon the tool that we're using to measure. So I could measure the height of everybody in class, and maybe I have just a yardstick, and it's hard to get a good accurate representation. So I may round up or down to the closest feet, right? So 4 feet, 5 feet, 6 feet, and so on. Or maybe I have a tape measure, right? And I could measure somebody up to feet and inches, right? So I can start to get fractal, but more specific. So I could say someone is 4'2" or 6'1" or something like that. If I had a laser, right, a measuring tool that was a laser, I could get up to a ridiculous degree of precision, right? I could say somebody is 5'7", 3, 6, and so on, right? So as far out as my measuring tool will take me. And you can have very large numbers, very large fractal numbers, but remember, we do think about them in terms of real limits. But anyway, if you're computing the range for a continuous variable, in parentheses, it's the highest score minus the lowest score, and then whatever that is, add 1 to it. So as you can see, the formulas here are quite easy. It's simple, right? It's easy to calculate. Well, I don't want to get ahead of myself, right? Let's just go ahead and give you a chance to do some examples. What I want you to do is compute the range for this small data set that I have on the slide right there, both as if it were discrete data and as if it were continuous data. And go ahead and do that. Pause the video. Try not to hurt yourself. And when you unpause the video, we'll go over the answer. So you should have done 12 minus 3, right? For discrete, the maximum value minus the minimum value. So you should have got a range of 9. And if we were pretending that this was continuous data, you would have went 12 minus 3, which is 9, and added 1 to that, right? Which would make the range for continuous data to be 10. Okay. So some advantages of the range is that it's very simple to compute, okay, which is pretty obvious. Some disadvantages is that the range is thrown off by outliers. We can't use the range in any future calculations that we're going to do. Like I told you at the very beginning of lecture, we're going to learn how to compute standard deviation, which is another measure of variability. And standard deviation is something that we're going to use in many of the formulas that we learn to run statistical tests in the future. And range can be tricky a bit because it doesn't always reflect the real variability that exists in a data set. So here's an excellent example of a couple of the problems with range, right? Let's just pretend that this was discrete data here, right? And if we were to compute the range of this data, well, obviously we would get 9, right? The maximum value minus the minimum value is going to give us the same values we got for the previous answer. But if we look at these data, right, it doesn't really jump out that 9 is really a good representation of the variability in these data. Two things are happening here. First of all, the bulk of the scores, right, 5 of the 6 scores are within 2 values of one another, right? So 5 of the 6 scores don't really have a lot of variability. What we have here is an outlier of sorts, right? That's affecting the range, right? It's skewing the range so that our actual mathematical total is a larger value of variability than what really I think is reflected in the bulk of the numbers in this particular small data set. So again, range is susceptible to outliers. And again, in this case, a very classic example where the range that we've computed doesn't really give a good measure of the real variability that exists in this data set. Okay. So I want to move on, sort of getting into standard deviation now, which is the more useful measure of variability. And to get to standard deviation, we're going to learn how to compute something called variance. And from our variance, we're going to learn how to compute ultimately our standard deviation. So standard deviation and variance, they both reflect the same thing, and that is how tightly or loosely clustered scores from a data set are around the mean, right? So the expected stress level for our class, the mean stress level for our class for stats this semester was 71.6. Okay. That's fine. It's a good measure of central tendency. But we also want to know, or we also should know that there was some variability between our scores. In what we're trying to ask when we compute measures of variability is how spread out are we around some measure of central tendency? Again, typically the mean. So we have a mean stress score, and here's our of 71.6, and here's our individual scores from the data that we collected at the beginning of the semester, and we can measure how much each individual score, each X value, if you will, each raw score differs from the mean, right, of 71.6 by subtracting the mean from each one of our scores, right? We'll get a deviation. Right? And the logic here is quite simple. Each of us deviates from the mean, some slightly, others quite a bit. So here I've just got the first 4 scores from our data set, and I'm subtracting the mean from each one of these, right? So the first person that we've reported here reported having an expected stress score in stats this semester of 80. And if we subtract from that the mean of all of our scores, we get a deviation of 8.4. So they were 8.4, I don't know, we'll call them stress points, I guess, 8.4 stress points above the mean. The next person had a 60. So 60 minus our mean of 71.6, it gives us a deviation of negative 11.6. So that particular person reported being expected to be 11.6 stress points below the mean, and so on. And note that the larger the difference, right? Like here's a pretty large difference, 50 minus 71.6. The larger the difference, the farther away a raw score is from the mean. So now we can begin to think about standard deviation and variance, and it's worth memorizing these two definitions. And you want to make sure that you understand them. I don't think you necessarily, I mean, hopefully you can memorize them. I mean, certainly you can put them on your note card for the exam that you're allowed to have, but I don't know. I think it's a bit of a waste of space. It's pretty easy to memorize. So standard deviation, the average or typical distance from the mean. Variance is the mean squared deviation. So ultimately, we're going to end up with a single number, right, that we're going to calculate that's going to allow us to answer what is the average deviation from the mean, right? On average, how far away, how many points, how many values from the mean do people tend to be? Now, in order to calculate the standard deviation, first, we're going to need to learn how to calculate the variance. And the variance is the average squared distance from the mean. Importantly, and I'll talk about this later, but the standard deviation is in the same units as the original data. And so what I mean by that is, let's say I gave you guys a task in the laboratory, like a simple reaction time task. And your job was to simply press a button that was placed in front of you as you're watching the monitor on a computer. You're told to press the button every time a light comes on, right, on the monitor, right? Every time something lights up on the monitor. So you're simply responding to the same stimulus over and over again every trial. It's a very simple task. It's a task that we've been doing since the 1860s. It was actually originally first done by Donders, who was an electrophysiologist even before Wundt's lab, which was the very first psychology lab in history. But anyway, it's a simple task. And if I were to take the average of everybody in the class, we'd probably get an average reaction time of about 220 milliseconds. Because again, people are pretty quick. And we'd have a standard deviation if we measure the variability. And this is my guess, because I've done several tasks like this. My guess we have a standard deviation around 110. Well, that standard deviation means 110 milliseconds, right? Remember, our mean was 220 milliseconds. Our standard deviation has been converted into the same units of measurement as our mean was, as our central tendency, measure of central tendency. So the standard deviation of 110 means a standard deviation of 110 milliseconds. So on average, the reaction time of this sample would probably be about 220 milliseconds with a 110 millisecond standard deviation. All right. Here's the formulas. Don't panic. I'm going to walk through the formulas. It's not so bad, right? If you're taking notes along with the video, which isn't a bad practice, get these in your notes. Let's see. I want to point out that the formulas are the same with a tiny exception for both samples and populations. Like I mentioned before, the difference is that we define our notation for population data, right, using Greek letters. So this is a lowercase sigma, right? It means standard or sigma squared means variance. Lowercase sigma means standard deviation. Where we use English letters, right? English letters for samples, right? So S squared means variance. S means standard deviations. I'll explain later on in lecture, right? Here are the two differences between the formulas. It pertains to variance. When we're computing variance for a sample, in the denominator of this particular formula, we're going to put n minus 1. That means the number of people in our sample minus 1. Whereas if we're computing variance for a population, big N is in the denominator of the variance formula. And that means all the people in your sample, right there. Or not sample, I'm sorry. That means all the people in the population. And also this calculating variance and standard deviation can be accomplished by breaking it down into a series of discrete steps. So to calculate the variance, first we're going to need to figure out what we're going to put in this numerator, right? We call this the sum of squares, and don't worry, I'm going to talk about that on the next slide. And then we need to put something in the denominator, either n minus 1 if we're computing variance for a sample, or n if we're computing variance for a population. Once we've computed the variance, right, then the standard deviation is nothing more than the square root of our variance. So this particular set of steps for these formulas are going to include three distinct steps. One is computing the sum of squares, which we'll talk about on the next slide. So you're going to do a formula, and you're going to get a value, and that value has to be placed in the next formula, right? The second step is computing the variance, which is all this. And then the third step to compute the standard deviation is simply taking the square root of the variance. Okay, so right, as of now, well, hopefully you've been keeping up on the readings, so you should know what sum of squares means. It's a term that we're going to see over and over and over again, right? There are two ways to compute the sum of squares, the definitional formula and the computational formula. And before I show you those slides, I'll just remind you or make you aware of the homework is going to require that you compute the sum of squares using both formulas. So these are the two formulas. We call them the definitional and computational formulas that we use to calculate the sum of squares, right? Which is going to be, again, let me go back one, the numerator, right? The numerator in the formula we use to compute the variance. The output of these formulas are identical, right? So if you had, a data set of 10 numbers, and you use this formula to compute the sum of squares for that data set, and then you turn around and use this formula to compute the sum of squares for that data set, you would get the exact same answer. So both of these equations will return the same value. If they don't, you're doing something wrong. Okay, so we're going to use both of these throughout the entirety of the semester. The reason why we learn two, simply put, is because there are you will often be computing the sum of squares for a variety of different statistics in the future. And sometimes there's a value in using one formula over the other because some of the interim steps that you use to compute the sum of squares can be useful for whatever statistical equation you're computing at that time. So as we go throughout the semester and we're using the sum of squares in future computations, I'll let you know which sum of squares formula you should use. But for now, we want to learn both of them. And in the homework, you're going to use both of them. And in the examples that I have for today, we are also going to use both of them. So the definitional formula is very direct and intuitive, right? It's simply the sum of our squared deviations, right? So For each one of our scores, we're going to subtract the mean from each raw score, square that difference. We're going to do that for all of our scores. And when we've done that, then we're going to add it up. And that will give us our sum of squares. So take each score, subtract the mean from each score, square that deviation, and then add them all up, right? Add them all up. Let's see, what else do I want to say here? The reason why we square each deviation, this is actually an important concept. If we were to just subtract the mean from each raw score and sum that up, I don't know, what do you think we might get? Well, the sum of x minus m, right? The sum of each raw score minus the mean, it's always going to equal 0, right? No matter how many participants, no matter how many numbers in our data set, or what the average is, if we were to just ignore this squaring right here and to just take the sum of each raw score minus the mean, we're always going to get 0. This is because some of our deviations are negative and some are positive, right? So if we're to add all those up, we're going to get 0. In order to do any meaningful math in the future, we need to get rid of those negative values. Now, we have two options, right? We can take the absolute value of everything, absolute value of our deviations, or we can square each deviation. That's what we're doing. We're using squaring. The reason why is the absolute values produce less accurate estimates around the mean. So remember that to ultimately find the standard deviation, we're going to take the square root of our variance. And because these initial differences get squared, just as they do at different stages in the computational formula, units of variance are not the same units as our original data, right? Remember, I talked about how standard deviation is in the same units as our data. Well, variance, right, that second step, if you will, are not the same units of the data because those data have been squared, right? So the standard deviation is reported as the square root of the variance, and the units then correspond to those of the data set, right? So in math, when you take the square root of something, you can undo that by squaring whatever sort of value you get there at the end. Okay, and then let's just talk a little bit about the computational formula. So here we've got it broken down into two clauses, and one of those clauses is, has a fractal problem. So let's just start with the clause on the left side. Sigma x squared. Well, hopefully you remember that from the very first chapter. What that's telling us to do is square each one of our x values, then sum them up. And what you're going to, and this is, you got to be very careful here, right? Because you want to make sure that you're keeping everything really, really well organized, right? So you don't get confused. So you want to square all the x values that you have, square all the raw scores, then sum them up, and write that down, and then you've done that part. Now let's turn our attention to the right side of the equation. This is sigma x in parentheses squared divided by n. So this is telling us to add up all of our x values. Once we've done that, square whatever that sum is, and then we're going to divide it by the total number of scores in our data set. Once we've done that, we're just going to subtract it from our sigma x squared, and that will give us the sum of squares. So again, to reiterate, if you had the same exact data set and you use this formula or you use that formula, you'll get the same exact answer for sum of squares. So notice, right, every single score in our distribution is used to compute the standard deviation and the variance, right? With the range, we only use the most extreme scores, right? The two most extreme scores, the largest and the smallest. So again, standard deviation is going to give us our typical distance from the mean. So first, we use either the definitional or computational formula to compute the sum of squares. Once we have that, we find the mean of the squared deviations, right? Make sure you're using the correct value in the denominator, right? You either want to divide, if it's for a sample, you divide sum of squares by n minus 1. If it's for a population, you're dividing sum of squares by n. Once you've computed the variance, you just take the square root of the variance in order to compute the standard deviation. So you have these three distinct steps. So we're going to do the definitional formula. We're going to do it on those original set of exam A and exam B scores that we looked at the very beginning of lecture, right? We saw these scores for two fictitious exams, but both of them had the exact same mean, median, and mode, which was 75. So we're going to compute the variance for those two sets of data. And we're going to use the definitional formula for the set of scores for exam A. But before I cut you loose to do that and then show you how I would do it, I want to just kind of reiterate it once more, right? So these are the steps that you should take to first compute the sum of squares. So the very first thing that you're going to need is the mean of all of your scores in the data set. Now, we already have that for exam A. It's 75, right? But you need your mean. So if you're computing a sum of squares using the definitional formula, if you don't know what the mean is, the very first thing you need to do is compute the mean. Now, when I'm showing my work, I find the best way to do this is to make two columns, right? A column that I call x minus m, right? Under which I'm going to compute each raw score minus the mean, right? That's why we computed the mean in our first step there, because we need it for the remaining steps. And then I'm going to have a second column, which I call x minus m squared. And so what I'm going to do under that column is I'm going to square each one of the deviations that I got in the first column, right? Now, once I've squared each of the x minus m deviations, well, then I'm just going to sum up that second column, right? That will be the sigma x minus m squared. Then, now that I have sum of squares, right, if I'm computing variance for a sample, I'm going to take that sum of squares divided by n minus 1. If I'm computing the variance for a population, I'm going to take that sum of squares and divide it by big N. Then after that, to compute the standard deviation, I'm going to compute the square root of the variance. Okay, here's the data from exam A, right? So you know the mean is 75. What I want you to do is pause the video, compute the variance, and compute the standard deviation using the same set of steps that I just gave you. And when you're done, I'll flip to the next slide and it'll show you how it should look. Okay, so I think this is a good way to show your work, right? This is what I just described. Here I've got the mean of 75. There were 8 points in the data set, right? N of 8, 1, 2, 3, 4, 5, 6, 7, and 8. And here in my x minus m column, I'm just subtracting this mean of 75 from each one of my data points, from each one of my 8 data points. And these are the values that I get. And remember what I told you, if you were to add this column up, you'd get 0. And it doesn't matter. Every time you'll get 0, right? It doesn't matter how many data points you have. It doesn't matter what these x scores is. It doesn't matter what the mean is. Anytime you just sum the deviations, you're going to get 0. And obviously we can't do math with 0, right? If we set our sum of scores, or sum of squares rather, with 0, if we divide 0 by another number, right, it doesn't work. So we need to square each one of these deviations, which I've done in this column. And then once we've done that, I go ahead and sum it up. And we're treating this obviously as sample data here, right? So here I am computing the variance. That's my sum of squares, which I just computed here, divided by n minus 1, right? So 8 scores minus 1 is going to give us 7. I get a variance of 168.29. Now I want to compute the standard deviation. So all I do is take the square root of this variance, and it gives me a standard deviation of 12.97. If you didn't get that right, you're going to want to pause the video right here, look at the work that I've done, compare it to yours, and make sure that you understand before you continue. Okay, here's the data for exam B, right? And what I want you to do is compute the variance and the standard deviation. But first I want to go over the computational formula, right? So one of the first things you need to know before you start computing sum of squares using the computational formulas, you need to know your n, right? You need to know your total number of scores. And we know that's 8, right? It's the same number of scores in exam B as there was in exam A. Also, columns are your friend, right? This is the way you want to do it. You want to create a column for all of the x values, right? So all these values here you want to write down and put in one single column. You also want to create a column that we call x squared. Here what you're going to do is simply square each one of these x values. and then you need to sum up both columns. So you're going to end up with a column that's sum of x, and you're going to end up with a column that's sum of x squared, right? Okay. Let me go back to the formula, right? I said you're going to end up with a column that's sum of x, and you're going to end up with a column that's sum of x squared. Now let's look at this formula again. So sum of x is right here. It's part of the equation. So when you add up all of your x values, right, from your column, then you've already done this part. And when you add up all of your x squared values, you've already done that part. So that's the nice thing about the way that I do this, right? These two columns already gives you two values, the two values that you have that you're going to plug into your equation. The last value you have is n, which you already figured out was 8. So by just summing the two columns, right, summing the column of x and summing the column of x squared, and knowing how many data points you have in your study, you've got everything you need to plug into this equation, right? So where am I here? Yeah, this is what we did last time. Here we go. Okay. But anyway, once you've done that, you want to just take the square the sum of x column, right? So square the sum of x column. Whatever that is, divide that by n. And now you're going to want to write that down because that's going to be, that's going to be the right side. I can change that right here. That's going to be the right side of your equation. There we go. And then whatever that is, subtract that from the sum of your x squared column. All right. I know it seems a little complicated, but, you know, if I were you, I would write down the computational formula because you're always supposed to show the formula anyway for all of your work, and then make these columns. And I think as you see how the values fit in to the equation, it'll make a little bit more intuitive sense. Anyway, here's the data. Give it a shot, and when you come back to the next slide, I'll show you how you should compute it. Okay, so we know our n is 8, so we've got that there. So here's all my x values, right? These are the original raw data, and like I said, I want to add that column up. That's sigma x, right? The sum of x, the sum of all my x values. Here I've squared each one of these respective values, right? I've squared each one of these respective values. When I do that, I want to sum them all up, and I get sigma x squared, right? This is the sum of each x squared x value, right? And I get a big number there. And so note our formula, right? It was sigma x squared minus sigma x in parentheses squared divided by n. Well, here's that sigma x squared in my formula, right? So I'm going to plug that value in. That's the left side of my equation. From that, I'm going to subtract sigma x squared, and I'm going to divide that by the total number of people in my data. So I do this, and I subtract it from this value, and I end up with a sum of squares of 40. But I'm not done yet, right? Now I need to compute the variance, which again is the sum of squares. Since we're dealing with sample data, the sum of squares divided by n minus 1. So 40 divided by 8 minus 1. That's going to give me a variance of 5.71. And to find my standard deviation, I'm simply going to take the square root of that variance. It's going to give me a standard deviation of 2.39. So again, if you've made a mistake, here's a good time to pause the video, or maybe even go back and listen to some things again, read the book, and see exactly where you may have made a mistake. Okay. Also, remember I talked to you about this idea that we do report our results whenever we do statistics, right? Because statistics are a part of science, and psychology is a science, and are one of our main governing bodies that defines how we state our results and disseminate our research to the public and to each other is the APA. And so throughout the course of the semester, just a reminder, we're going to learn how we present our results in APA. So whenever you write up a results section, right, for your research methods class, or if you decide to go on to a career in science, you always report the means and standard deviations, and you report them at places where you're actually talking about that particular level of the variable. And you should always report them in italics, an M for mean and S for standard deviation. should be in italics. All of this is in parentheses. So here's a sort of example of what we just did. Of course, we haven't ran a statistical test, so this is all I can really say about these two data sets. But I'm saying something to the effect of, although students scored the same on both exams, variability was higher for exam A. And note, here's where I open up a parentheses and report the mean and standard deviation for exam A. So this is what we figured out earlier, right? So the variability was higher for exam A. So as soon as I say the level of the independent variable, I report its respective mean and standard deviation, right? And then continuing on. Compared to exam B. And note, here's the mean and standard deviation for exam B. So note that they're in parentheses. The M is italicized. The S is italicized. The other things are not, right? The number is not, the comma is not italicized, the equal sign is not italicized, only the letters, right? So, that's, you should know how to report this in APA. It's part of the assignment. You'll have to do it a lot. It's part of being a psychology major. All right, typically this is the time that I would ask if you have any questions. You should understand some conceptual meanings and calculations of things like sum of squares, variance, standard deviation. You should know stuff about the range. You should know which formula we use in the range. So these are some things, hopefully, that you should as you do the homework and maybe do the practice problems, that you start to get comfortable with. But you will get comfortable with it as the semester goes on. Okay. So remember, I want to bring it back to the sum of squares the variance formula for a sample, right? When calculating variance for a sample. This is why we divide sum of squares by n minus 1 when computing variance for a sample. So this n minus 1 correction has to be done when we're computing variance for a sample. Because when we select a sample from the population, right, when we randomly select a sample from the population, we're more likely to select individuals who are relatively closer to the mean than we are to select individuals at the extremes of our population, right? Why is that? Because more individuals exist near the mean, near the middle, right? So if we randomly pull people to be in our study out of a distribution that looks like this, well, most of our people are in here, whereas very few of people that we could possibly select are in these extremes, are in these tails, right? So we're more likely to underrepresent the overall variability of the population because the sample that we've selected is a little bit more representative of the middle of the population and closer to the mean. So as a result of this, right, our variability is going to be less. Our sample variability is going to be less than our true population variability. So if we don't correct our degrees of freedom, right, which is what we call this, our degrees of freedom, the denominator of our variance for samples, if we don't correct our degrees of freedom to n minus 1, right, if we don't divide it by n minus 1, we create a bias where we either under or overestimate population parameters. So remember, with inferential statistics, we're trying to use a sample to draw conclusions about a population. Our sample variance and our sample standard deviations, they're estimates of the variance and standard deviation for the population, right? So if we don't correct for this bias, it's a problem. So by dividing the sum of squares by a smaller number, we end up getting a larger, more accurate estimate of the population variance and standard deviation, right? So these unbiased estimates equals the average value of the statistic being equal to the population parameter, right? The average value of the statistic obtained from all possible samples of a specific sample size, right? So that's why n minus 1 degrees of freedom, we use it to correct for bias, given the possibility that our sample is an underrepresentation of the true variability in our population. Okay. Now, we also want to think about standard deviation, and this is an idea that really starting in chapter 5 through, I think, chapter 7 is a concept I'm going to revisit quite a bit. But we can think about properties of the standard deviation by examining these properties as they would fit on a symmetrical normal distribution, right? Where you have this. So again, if you were to fold this in the middle, this distribution, both halves would be identical, right? And you say, well, why are you bringing up this example? Well, it's kind of funny, and again, we'll get more into this as the semester goes on. But the basic idea is this. If I select a large enough sample size for one of my experiments, if I select the appropriate and large enough sample size, then it doesn't matter what my distribution comes from. My sample, right, should better approximate my population mean. And if my sample size is large enough, right, the means of all possible samples that I could compute will tend to start to look like a normal distribution. Now, don't worry about this too much. Again, I'm sort of foreshadowing here, but I want to use this as an example to talk about the different properties of standard deviation. So assuming we have a normal symmetrical distribution, right, we could say, okay, this is the mean, right? This is the most central point. And from here to here is one standard deviation above the mean. From here to here is the difference between 1 and 2 standard deviations above the mean. And anything from here to the very end is 2 standard deviations beyond the mean, above the mean. And so this is all the same for the opposite side as well. So if we were to sum up these two, right, these two sections, if you will, these two areas, it represents -1 to +1 standard deviations of the mean. And roughly what? 68.2% in a normal distribution, 68.2% of all our scores, almost 70% of our scores fall within 1 standard deviation of the mean if we're dealing, again, with a normal distribution. If we go all the way out from -2 to +2 standard deviations, that's around 95% of all of our scores, right? We'd add these two, right? So basically add all 4 of these areas together, and we get something very close to 95% of all of our scores we would expect to fall within -2 to +2 standard deviations of the mean. Typically, anything that falls into these tails, right? So anything above +2 or below -2 standard deviations of the mean, typically we would think of that as an extreme score. So if you're given the mean and standard deviation of a distribution like what we have here, and then you're given a raw score, right? You can ask of that raw score, is it an extreme score given this mean and this standard deviation that this score came from, right? All right. So here we're trying to figure this idea out. Here we have a mean of 170, a standard deviation of 15, and I'm asking you, is 180 an extreme score? What do you think? I'll pause for a moment while you ponder it. Now, one of the ways that you can figure this out is you can start at this 170 mark, which is the mean, and you can continue to add 15, right? If you added 15 to this, you would get 185, and that would be 1 standard deviation above the mean, right? If you added 15 more, right? If you added another standard deviation to that 185, it might be over here, right? That would be a raw score of 200. So we're asking, is 180 an extreme score? The answer to that question is no, because 180 would be within 1 standard deviation of the mean. Remember, we said that anything that is more than 2 standard deviations above or below the mean is something that we would consider an extreme score. Let's look at this raw score of the distribution, right? So mean of 170, standard deviation of 15, same thing as before. And we're asking, is 120 an extreme score, right? So we can start with 170, right? And we're going to subtract 15 from that, right? We're going to subtract 15 from that. And that's going to give us a value of 100 and, wait, what is it? 155. So roughly, the raw score of 155 is one standard deviation below the mean. Well, 120, we're asking is it an extreme score. Does it fall in that range between 155 to 170? The answer is no. So let's subtract another standard deviation. Let's go out to -2 or 2 standard deviations below the mean. So 155 minus 15, that's going to give us 2 standard deviations out somewhere around here. That's going to be 140. Still, we haven't fallen, our score here that we're testing hasn't fallen into our range. We're now 2 standard deviations below the mean. If we keep going any further, we're going to get into extreme territory, right? If we take another standard deviation, if we go another standard deviation all the way out to 3 standard deviations of the mean, so we subtract another 15 from that 140, we get 125. So the score of 120 is more than 3 standard deviations below the mean. So of course it's an extreme score. As I said in the previous slide, anything more than 2 standard deviations away from the mean is something we would consider an extreme score. And why do we consider it an extreme score? Because like we've shown up here, in a normal distribution, 95% of our scores have a probability of falling between -2 and +2 standard deviations, right? So anything that falls out into these tails has a less than 2.15% chance of occurring in each one of these tails. We would consider them an extreme score. Okay. So you also might be asking, sort of generally speaking, is variability good or bad? So remember, the goal of inferential statistics is to detect meaningful and significant patterns in research data. And so what we're asking is, do patterns observed in sample data reflect corresponding patterns in the population? Or are our observations simply random fluctuations that occur strictly by chance? Well, variability plays a critical role in inferential statistics because variability in the data influence I would say ease, really, at which we can detect patterns. So in general, low variability means that existing patterns can be clearly detected, or more easily detected, I guess I would say, whereas high variability in a data set tends to obscure patterns in the data. So let's look at an example, right, where they have 2 different drug treatments in which the mean of each group differs by only 5 points. And what we're asking here is which of 2 drugs, right, which of these 2 drugs that we're testing here, or treatment 1, treatment 2, are better at reducing symptoms of something. I don't know, it doesn't really matter. So, can we detect the difference if there's a small amount of variability in each group? The answer is likely yes, right? Even though we haven't learned how to statistically evaluate the differences between 2 means, this low intra-group variability, right, the variability within this group, and the low variability within this group, right, and the fact that there's distance between the measures of the histogram of variability, it suggests that we would likely find a difference between these 2 means. So on average, the scores in treatment 2, right, they're 2 to 5 points higher than the scores in treatment 1. So this 5-point difference or so is relatively easy to see when the variability is low. Well, what if we have large variability, right? So look what's happening as in the case of experiment B, or I'm sorry, treatment 2. Yeah, experiment B, treatments 1 and 2. I don't know why I got lost there. Here are the means, right? They're exactly the same as they were in experiment A, right? The means are the same. However, the dispersion of scores is far more spread out, and it overlaps, right? It overlaps a great deal. So this high variability, it obscures any patterns that might exist in the data, right? It makes it hard to detect a significant statistical difference. So in summation, some variability is necessary, right? For sure. If you didn't have any variability in your experiment, then there really isn't anything to measure, right? There's nothing to talk about if everybody has the same score. So some variability is necessary, but too much variability can obscure differences between groups. And remember what I said in chapter 2, right? I'm up to about, 15 papers now. I'm a very active researcher at my university. The very first thing I do, just like I said in chapter 2, when I have my data, is I plot a histogram. And that histogram gives me a visual representation, not only of the shape of my data, but it tells me right away how my data is spread out. It gives me a good visual sort of sense of the variability in my data. I think there's a couple of questions like this on the homework. I just want to make sure you understand it. There may be times when you want to transform scores, right? Like if you're measuring something in minutes, but you want to transform it into seconds. You should know what transformations like that do to the standard deviation. Because remember, we learned that adding a constant to a value to the mean and the median, right? It wouldn't change if we add a constant to every score, right? It would change the mean and the median by that exact value, right? So if we added 5 to every single score, both the mean and the median would increase exactly by 5. Remember here, standard deviation is a measure of distance, right? So if we add a constant to each score, it's not going to change the standard deviation, right? It's not going to change the standard deviation because it doesn't change the distance between scores. Say you got 18 on the homework, your friend got a 16. That's a difference of 2, right? And let's say for whatever reason I decided to add 2 points to everybody's homework. So now you get a 20 and your friend gets an 18. But it's still a difference of 2, right? The dispersion between scores doesn't change, right? Adding a constant is going to move each score. The entire distribution shifts to a new location in a sense, right? But it doesn't change the overall variability. If you multiply by a constant, right, it changes the distance between scores. And it changes it by a factor of whatever you're multiplying, right? So again, you get an 18 and a 16 on the homework, right? You and your friend, you multiply each score by 2. So now it's a 36 and 32. Before the difference was 2, now it's 4, right? So multiplying each score causes the distance to be multiplied or changed by a factor of that amount. Okay, so that's it. Here are some practice problems from the back of the chapter. I think everything except question 2, there's an answer to it in the back of the book. So the answer for the even questions, or I'm sorry, the odd questions are at the back of the book. And that's it for the lecture today. I shall see you next time.